this is Ms. DB. In this video we are going to learn more about rational functions and review what we've already learned about them. So to start with, we've got this parent function over here of y equals 1 over x, and it will have a vertical asymptote at x equals 0, and it'll have a horizontal asymptote at y equals 0. And that's kind of the most basic parent rational function that you can have. Rational functions are also sometimes called inverse functions, or there's another word that'll come to me. This is an example of a rational function that has been transformed. So this one has been translated, and it has been translated 2 units right and 3 units down. So then your vertical asymptotes are at a different place. In this one, the vertical asymptote is at x equals 2, and the horizontal asymptote is at y equals -3 because it went down. We also will be asked to find the domain and range of a rational function, which the graph of a rational function is called a hyperbola. And to find the domain, it'll be all real numbers except where the vertical asymptote is. And the range will be all real numbers except where the horizontal asymptote is. So you have to make sure that you say that it's everything except for that value for the domain or for the range. Also, from the equation we can find the asymptote, so it's not just from the graph, but we can look at this and we can use the denominator to find the vertical asymptote. We cannot let x be -2, because if it was, we would be dividing by 0, which is not allowed. And that gives you the vertical asymptote. X equals -2 is the vertical asymptote. The graph can never be that, so it'll approach that, but it'll never reach it. And then in this one, the horizontal asymptote is given from the number that has been added. So this one has been moved up. So instead of y equals 0, it's y equals 4. The end behavior can also be found from the graph. The end behavior, as x approaches infinity, so as x gets bigger and bigger and bigger, we can see that the graph is approaching the horizontal asymptote. So the graph, or y, is approaching 4. And as x gets smaller and smaller and smaller, it gets more and more negative, we can see that the graph is going to approach that horizontal asymptote from the other side as well. So it's approaching 4 from that side as well. So they won't approach infinity or negative infinity in most cases. A rational function is called discontinuous because it has gaps or breaks, and most of them are discontinuous. If it was continuous, it would have no gaps or breaks, and we've talked about that before. And linear, quadratic, polynomial, exponential, those are all continuous functions, but this is discontinuous. This is another example of a rational function here, but this one is not called a hyperbola because it doesn't have the same kind of symmetric looking shape. This one is made by a little bit more complex function. We've got a little bit more going on in the numerator than before. In this one, we can use the numerator, this is in factored form, to find the roots or where it's crossing the x-axis. So sometimes you'll be able to find those solutions or those roots from the numerator. The denominator will still give you the vertical asymptote. And so in this one we have x equals -1 will be the vertical asymptote. This one does not have a horizontal asymptote because the two branches are doing two different things. Also, the end behavior is different in this one. We have, as x gets bigger and bigger, the branch on this side is going to approach infinity, and as x gets smaller and smaller, this branch is going to approach -infinity. So that's different than the more standard hyperbolas that we looked at before. These are some notes. Let's see, we talked about most of these except the y-intercept. Sometimes it'll have a y-intercept and sometimes it won't. This one does have a y-intercept right here, but it doesn't tell us much information. Also, they will either be concave up or concave down, the different branches. They won't switch because of that discontinuous. So this branch over here is concave down, this branch is concave up, but there's no point where they meet at an inflection point to switch. The change happens where there's an asymptote. So each branch will either be concave down or concave up, but there won't be an inflection point in rational functions. And make sure that you change your scale so that you can see all parts of the graph. They'll always have more than one graph. There's an example on, did I put this here? Yeah, look at number 2 here has 3 branches. So there'll always be more than one branch. So make sure that you're not looking at a zoomed in part of your coordinate system so that you didn't see all of them. So zoom out a little bit, make sure that you can see everything before you start copying and pasting the graph or answering questions about it. So all you have to do for this assignment is there's 2 rational functions that are graphed, and you're going to answer a bunch of questions about them, and then there are 2 that you're going to graph, and then there are 2 that you're going to graph that will have similar questions, but you'll be making those graphs. You can make the graphs on your graphing calculator and then copy what they look like here, or you can make the graphs in Desmos and then paste them into the worksheet if you prefer to do it that way. Let's look at number 2. The domain, my computer's acting up a bit here, so we'll try to get this completed. The domain for number 2 is not all real numbers because there are going to be some gaps. There's a gap here and there's a gap here. There's 2 vertical asymptotes for this one. So let's find out the asymptotes before we try to do the domain. And you could graph this and then you could find it a little bit closer, but I think I'll be able to 1, 2, 3. This looks like at x equals 3 there's a vertical asymptote, and at x equals -3. So there's 2 vertical asymptotes in this one. So the domain is going to be all real numbers except x cannot equal 3 or x cannot equal, maybe it should be negative, maybe it should be and, I don't know, my grammar there. And the range, okay, the range is pretty much everything. The range is everything positive, everything negative, and this one, because it is a continuous branch, I guess you'd call it, the range can be all real numbers in this one, which is unusual for a rational function. This one, like we talked about, has 3 branches, also unusual. Now, there is a horizontal asymptote. It does not apply to the middle branch, but there's a horizontal asymptote for this side and for this side, and it is that y equals 0. It's okay that this one goes through the horizontal asymptote because these 2 branches do use that horizontal asymptote to guide what they're going to do. Y-intercept, let me erase my mark so I can see what was originally there. Looks like the y-intercept is at 0. X-intercept, there's none here, there's none over here, but there's also an x-intercept and a y-intercept at the same point, so there's 1 there. Symmetry. This does seem kind of symmetric, doesn't it? We've got a branch on this side, we've got a branch on this side, and then we have this figure in the middle. It looks like if we were to take our graph right here and cut it, and then rotate about that point, it may look the same on either side. If we rotated this 180 degrees, would it look the same? I think it would. So I'm going to say that there is symmetry about a point. It looks like it's about the origin. So you could say that too. Or you could say rotational symmetry 180 degrees. And the end behavior, this one's an interesting one for end behavior, is x gets bigger and bigger and bigger. This function on this side is going to approach the horizontal asymptote of y equals 0. But also as x gets bigger and bigger and bigger, this will approach negative infinity. So that's something to consider. And on this side, as x gets bigger and bigger and bigger, this graph farthest on, or this branch farthest on the left will approach 0 again, the horizontal asymptote of y equals 0, but this part will approach infinity. So you might make a note that the middle branch is different and will do a different thing than the other two branches will, and that will be approaches infinity and negative infinity. Alright, that's enough for rational functions. You do have a couple more problems to do. Let me know if you have any questions.